Alcock-Paczynski effect, but the Alcock-Paczynski effect applies to a lot more than just the BAO signal. So we can use the fact that we know that the universe should be isotropic and homogeneous to make cosmological measurements. If we use the correct cosmology to convert basically redshifts to distances, then we should have statistical symmetry, not just in terms of BAO, but in terms of everything. And it turns out that to get this, we need h times dA to be right. So if we think of a spherical object, then there will be a redshift distance across that object. If those redshifts are telling us about the Hubble flow, because the expansion rate at the edges of that object are different. That delta z will define the size, the apparent size of the object along the line of sight. Then if we look across the line of sight, there is the angular diameter distance that tells us the actual size from the apparent size of that object. And even if we don't care how big that object is, if we convert redshifts to distances using a cosmological model that has h times dA right, we will see that object to be spherical. If the individual components are different, we would see that object as being bigger or smaller than it actually is in the universe. But usually, for most objects, we don't actually know what their physical size should be, but we do know that the universe should be homogeneous and isotropic. So if we stack enough objects such that we get rid of all of their individual features, we should have a spherical stack in the end. This applies to clusters of galaxies, it applies to voids. It applies to anything that is large enough that the expansion of the universe is still dragging that object. Basically, it's still expanding that object. And a lot of people get difficulties with the Alcock-Paczynski effect when you look on small scales, and I'll explain what's happening there later on. So we've already seen the Alcock-Paczynski effect applied to BAO. For the BAO to be a spherical ring in this plot, we had to have basically converted the redshifts into distances using a cosmological model with the correct h times dA. For flat cosmologies, lambda CDM cosmologies, here's the Friedmann equation. It only depends on matter, omega matter. And h times dA basically normalizes out the Hubble parameter, and it leaves you with a dependence only on omega m. So the Alcock-Paczynski effect is a very good way of measuring the matter density in the universe. The problem is that structures grow and they stop expanding with the expansion of the universe. So here's a plot. It's pretty simple and quick to make. You take a cosmological simulation and you look at pairs of objects. You bin in pair separation and you look at the pairwise velocity, basically the velocity inwards of every pair of objects in a simulation. And you will end up with a curve like these dots coming from the simulation. If all of the pairs of matter particles, galaxies, whatever you've chosen to do, were expanding with the co-moving expansion and there was no actual growth of structure, everything would lie along this co-moving line here. If instead you had objects which were fixed in physical coordinates, like this room is not expanding with the expansion of the universe, then you would have static objects, their velocities would be exactly that in co-moving units that would be required to basically stop the co-moving expansion from happening. And so what you see for pairs of objects is that they start off with a linear velocity towards each other, they go nonlinear, they turn around, and then basically they head towards this fixed solution where they are static objects. If they are static objects, then any delta z across them will just tell you about internal velocities within that object. It will not tell you anything about the Hubble expansion rate across that object. And so if you want to do the Alcock-Paczynski effect, you need to work in this regime where you have a hope of basically understanding the rate at which objects are moving together. And you can think of this as basically redshift space distortions. Everything for a pair of galaxies that means it doesn't fit on this co-moving line, you can think of as being a redshift space distortion against the Hubble expansion rate, giving you a combined velocity. So here you have an extreme redshift space distortion, which would exactly cancel cosmological evolution. If you looked at simulations of different cosmologies, you would find a different curve here, but you would find that everything is still tending towards a static solution because that's what the universe is doing. It's creating patches like this room that are not expanding with the expansion of the universe. So this sets a fundamental limit on the size of objects that we can use the Alcock-Paczynski effect for. There are two ways of thinking about this. There's a Newtonian way where you've got basically the expansion of space happening as a background, and then you've got objects basically having peculiar velocities towards each other within that framework that would make them static objects with all of those objects. Or you can think of a more general relativistic type of picture where you have these spaces living in static space-time. Basically, the idea, you've all done spherical top hat collapse, hopefully. Different patches of the universe, different initial conditions. You can treat them all as mini-universes. In this case, the mini-universe would be one that had collapsed, virialized, and formed a static space-time rather than the overall average universe, which is behaving with the background parameters. So small objects can't be used for Alcock-Paczynski tests. There have been some claims in the past, a famous one that I won't reference, but it tried to do Alcock-Paczynski effects using pairs of galaxies. This just fundamentally will not work. Okay. So the Alcock-Paczynski effect is an anisotropic effect. The redshift space distortions are an anisotropic effect. You might worry that basically when you try to measure both, you're going to have a degeneracy. You're going to have a problem getting both sets of information out. That is in fact true, but there are various things that help you. And in detail, the way that the Alcock-Paczynski effect changes the quadrupole compared to how redshift space distortions change the quadrupole are quite different. This is a plot taken from this paper by Beth Reed. What she did was to look at different models that had the same, roughly the same monopole, but different Alcock-Paczynski quadrupoles, and showed that basically they have structure in them, whereas RSD would just be basically moving all of the quadrupole up or down. The BAO signal definitely helps you measure the Alcock-Paczynski effect separately from the redshift space distortion effect. Another way of thinking about this is that the redshift space distortion effect is increasing the overall amplitude of the power spectrum by adding in this velocity component. This velocity component, because it's, we saw the velocity power spectrum is related to the overdensity power spectrum. Any features in the density are there in the velocity. So when you add in this component of the velocity power spectrum, everything goes up or down. Whereas the Alcock-Paczynski effect is at physical scale. You're moving things in scale. Basically, you're saying if I get this wrong, what was at this separation along the line of sight is now squashed in. And so that would be moving the power spectrum left or right. Redshift space distortions moving the power spectrum up or down. The power spectrum is close to being a power law, so this is close to being degenerate, but the power spectrum is not a power law in detail, so you can break that degeneracy. Okay. Everybody good? It's getting late in the day. You've had a very long day. You all right? Okay, good. So one of the key objects to use for Alcock-Paczynski measurements are voids. Voids are places in the universe that are very boring. They have very few galaxies in them. But they are very big, and they're expected to be expanding with the expansion of the universe. So they can be used as standard shapes and can be used to make these Alcock-Paczynski measurements. If you look at any one void, it does not look spherical. But if you stack enough of them, thanks to Copernicus, we kind of know that they should look spherical in the end. The other good thing about voids is that it's allowed a lot of people to try and figure out how best to find them. There are many different algorithms, watershed algorithms, spherical finders, where you just basically smooth the field with a spherical filter and you look for peaks, look for troughs, and so on. Rather than looking at the galaxy-galaxy two-point correlation function, we look at the void-galaxy correlation function. In fact, the void center galaxy correlation function. You can define it and think about it in the same way. But now when you're stacking voids, the void center galaxy correlation function really is just an average profile of the voids you're looking at. The galaxies are telling you the profile of the void from your void center. Therefore, the number of pairs of void center galaxies that you have is just telling you the profile of the void. And so when you calculate the void galaxy cross correlation for your whole sample, you're looking at the average profile of your voids. All right, complete tangent. I had this tangent, not now, but when I was writing the slides, and I was thinking, there are really three stages of a new technique, like voids, like whatever else you want to do, some sort of nearest neighbor statistic or some sort of new technique to measure the Hubble parameter that I'll talk about later. There are three distinct stages. The first is the idea itself. It's almost always released in a paper, which is overhyped. There are huge claims about how good the technique will be, usually backed up with dodgy Fisher matrix calculations. Don't quote me on this. I've done papers like this as well. The next stage is that the first analyses appear with simple techniques, and they're almost always providing weaker results than expected compared to the Fisher matrix predictions because real-world things have got in the way. And then the third stage is that it's realized that things are really a lot more complicated than anybody has previously thought. We need complicated techniques to get rid of all of these systematic problems. A new language has been developed in the teams developing the work, including an awful lot of acronyms about different aspects of it. There's an increasing reliance on simulations or machine learning to do the hard work of understanding what's going on. And there's increased concern about systematics, and basically grad students are brought in to do all the worrying. So voids is at stage 3 of this. And two key problems are that void finding is very difficult to model. So if you want to look at RSD Alcock-Paczynski effects with voids, you have to worry that the voids themselves might be biased by how you're finding them and the effect of redshift space distortions and Alcock-Paczynski on those voids themselves. So let me give you an example. Suppose you use a spherical void finder, which means you're finding voids by smoothing the field with a spherical filter, and you're looking for troughs, really low points, and you're going to call them void centers. But now suppose you're doing that on a field that still has some redshift space distortions in it. Then that spherical void finder is going to preferentially find voids that have a very low amplitude of redshift space distortions, because they're going to find spherical voids, whereas actually your voids are going to look a little bit extended along the line of sight. So now when you model them, you have to allow for the fact that if you've got the redshift space distortion model wrong before you find the voids, your voids are now biased in some way, and it all gets very complicated. Now we think we know the answer to this one, which is to do reconstruction before you find the voids, and for the same way that it moves all of this structure back, it helps remove the RSD effect from void finding. But it was recently realized, and we're now in 2024 paper by a PhD student, that the Alcock-Paczynski effect is similar, and in fact even slightly more complicated, that if you do the cosmology wrong, then find the voids, do one of these spherical void finders, you have this bias on the actual Alcock-Paczynski effect when you find those voids. Really what this means is that you have to do things iteratively. If you want to test a model with a particular Alcock-Paczynski effect and redshift space distortion effects, you need to put that in before you find the voids. The only problem is that void finding takes an awful long time, and you don't really want to have to do it for every model you have to test. And now we're in the realm of, well, let's have an emulator. Let's not worry about doing the actual model analytically. Let's just worry about how the simulation can do it. Question at the back. The question is there a higher likelihood of a void near a cluster? No, is I think the simple answer. If we go back to one of these maps of structure in the universe, you can pull out and see where you hopefully would find the voids, and you see that they're ringed around by an excess of structure. And I'll show you a void galaxy correlation function later on, and you can see that there are basically zero, like their density is -1 in the center, the overdensity, so the density is 0, and there's a little wall around them, and those walls would be where you find the clusters. Okay. So back in stage 2.5, people were doing void analyses. This is, again, SDSS BOSS analysis, add a series of different redshifts. These are the monopole moments of the galaxies around the voids. You can think of this as being an average void profile. They go down very close to -1 in the center, showing that there is absolutely nothing there, and they have this wall around them where there's an excess positive density. And then the quadrupole is basically a combination of the redshift space distortions together with the Alcock-Paczynski effect based on the difference between the truth and the fiducial cosmology that you used. And this is slightly different. You can actually use, in the voids, we think you can use a linear model to go between the nonlinear overdensity that you can measure and the nonlinear velocity field that can remove the RSD or put the RSD in the model. And you can measure F sigma 8, this basically RSD growth factor from the voids. It's not quite as good as measuring the RSD from the galaxies. But what's really interesting is that the Alcock-Paczynski effect is actually stronger from the voids. The measurement is stronger than from the baryon oscillations. So there's a good reason that if we can figure out all of these nuances and get the systematics to a level where we're happy, then actually for the Alcock-Paczynski part of the cosmological measurements, voids can do better than BAO. And if you can think of some other way of finding some other object in the universe that would have this property of being a standard shape, then I think there is even more information to be gained from this kind of technique. And this comes back to the plot I showed reasonably early on in the previous earlier lecture, where I showed the information content from the bispectrum was going up above the nonlinear and linear power spectra on small scales. This is the reason why. It's the fact that when you have higher order terms, you build up things like voids, and then the projection effects from things like Alcock-Paczynski give you this extra information. Okay, any more questions on Alcock-Paczynski? Okay. Let us talk about the Hubble parameter. This is the last piece of information from my gold mine I'm going to dig from a galaxy survey. And I'm going to give you my own personal biased view of the Hubble parameter, ending up with some interesting new techniques that we've been developing in my group, which is why I put this in this lecture. Okay. So from the start, the Hubble parameter has had a long history of incorrect measurements. Hubble, who is famous for actually finding this relationship, got his galaxy distance estimates wrong by a factor of 7 and measured the Hubble parameter to be 7 times larger than we now think it is. This set the scene for a large number of Hubble parameter measurements over the years, all claiming smaller error bars than they probably should have done because they didn't know what was going on. In fact, in the 1980s and the 1990s, where almost certainly none of you were born, we had the Hubble wars. Not a Hubble tension, a war, which must have made the conferences a lot more interesting than present day. In fact, we had de Vaucouleurs claiming the Hubble parameter was 100. We had Sandage and Taman claiming it was 60, and both using similar techniques, fighting vehemently about it. And then the HST came in, Wendy Freeman did her analysis, the Hubble parameter came down to in between the two groups. War never leads to a winner. And we ended up with the Hubble parameter of around 72. There was a period, a glorious period of peace in the Hubble saga, which was recently broken due to this divergence, as you're all aware, between low redshift distance ladder observations and cosmological observations, which favor lower or higher values. Noting that the difference in this Hubble tension is significantly lower than the difference in the Hubble war. Look it up. I was doing this slide. I didn't realize it was called a war. It's brilliant that it's called a war. Okay. All right, so we've got the current Hubble tension, very minor skirmish compared to the war. Local measurements versus large-scale measurements. What's going on here? Well, all Hubble parameter measurements have to start with an absolute calibrator. The Hubble parameter is in units of inverse time. It is an absolute measurement. That means you have to start with some absolute measurement. You can start with the Earth-Sun distance, but then you have to move it out to cosmological scales. And why do you have to move it out to cosmological scales? Because you want to measure the expansion of the universe. You don't want to measure the expansion of the solar system or the expansion of the local group. You want to measure something over a cosmological volume. So if you want to do this using actually the distance redshift relationship, you want a set of objects where you know the distances and the redshifts, you have to build it up going out to nearby galaxies, to slightly further away galaxies, and finally out to a cosmological volume with supernova. If you want to measure Hubble parameter from the CMB, you also need an absolute measurement. And the absolute measurement from the cosmic microwave background is its temperature. Because the CMB is a black body spectrum, from the temperature, you go to a photon density. If you've ever wondered why Planck is telling you the present day baryon density, even though the CMB is a projection of the last scattering surface at very high redshift, it's because those CLs only tell you ratios, abundance ratios. They tell you the ratios of baryons to photons. They tell you the ratio of dark matter to photons. To normalize it, you need the CMB temperature, and you need to know the present day density of photons. Going off on a tangent again, where was I? Oh yeah. So once you know this, basically you know omega mh squared. You've had the lecture on how all of these different degeneracies in the CMB, all of the different parameter dependencies in the CMB depend on each other and give you the different measurements. From this, you can go through to a measurement of the expected present day expansion rate in H0. But this all comes from the CMB temperature. Oh, okay. I had a slide on that I'd forgotten to put in. You get this omega mh squared degeneracy for flat models. You can break it with peak heights. You do that, and you find low values of H0. It is not just the CMB that is giving these low values of H0. If you take the BAO positions, then you get a parameter degeneracy between the baryon density, the cold dark matter density, and the Hubble parameter. All you need to break this degeneracy and measure H0 is a measurement of the baryon density, And you can get this not from the CMB, but from looking at Big Bang nucleosynthesis, which tells you what the baryon to photon ratio is. You can use the CMB temperature to give you the photon density. You can get the baryon density. This is enough with the BAO measurements to measure H naught. And this gives you a low value of H naught. This is it for Sloan. Again, I should have updated this to DESI, but you can see here, this is the BAO. This is BAO plus BBN. It agrees remarkably well with the H naught value you would get from the CMB alone. It does not agree with that you get from the distance ladder. So something funny is going on. It's not just a local distance ladder against CMB. It's more like a local distance ladder against measurements that use more universal measurements, more universal quantities. And so an interesting question that one of you should be asking is, have we got the CMB temperature wrong then? And the answer is that to solve the Hubble tension by changing the CMB temperature requires like don't trust this number, but like a 10 sigma shift or something from the Kobe value. It's a huge shift that's required in the CMB temperature to do this, i.e. we know the CMB temperature a lot better than is required to give us this high value of H naught. So these are now increasingly not like recent measurements because it's now 3 years old, this plot. But this is basically what you've got. You've got low values favored by low redshift measurements of cosmology, high last scattering surface measurements of cosmology versus high values from Cepheid variables. So what's happening? Well, who knows? Hopefully one of you will figure it out. I'm getting too old to figure things out. I sit on boards and panels and have meetings these days. All of these start with an absolute measurement, because H naught is an absolute quantity. All of them empirically link them to, or theoretically or empirically link them to observed physical quantities. All then make distance observations on cosmological scales as they should. Nobody has yet found a smoking gun that says this is what's gone wrong. And indeed, each component could be wrong. We know a lot of things that it's not. We know that it's very difficult to mess with the low redshift universe. Here's a visual representation of the Hubble tension. These are the BAO measurements from SDSS. I should update this one as well for DESI. This is the way you want to get to. And so can you just push this curve up steeply? The answer is no, because this low redshift measurement didn't just come from redshift 0. It came from a whole range of redshifts. And it gives you a whole slope that would not work if you just shot this slope up. And this next plot is supposed to show this. This is basically the low redshift distance modulus measurements showing you that they're not just at redshift 0, they actually cover a range of redshifts. And if you start to mess with them, the residual will go wrong as you try to increase that slope. The low redshift distance ladder measurements look very much like, in terms of shape, the BAO measurements. It's just that they end up with a calibration that gives them a very much higher value of H naught in the end. Is there a period of early dark energy? It is incredibly contrived, this solution. You have to put in a very small amount of acceleration between matter radiation equality, because you don't want to mess up Big Bang nucleosynthesis or what's happening in the early universe, and decoupling, because you don't want to mess up the production of the CMB. But if you basically put this bump in, you can change that integral that we saw before for the sound speed, the sound horizon. You can put an extra piece in that integral, right? So you can change that sound horizon at recombination and make it bigger. And in this case, you can then shift all of the CMB and the BAO measurements, and you can get a higher H naught. In principle, this is a way of doing this. In practice, and this is a good reference paper for this, in detail, things break down. all of a sudden the way in which you're putting in this acceleration and the exact way that it's changing decoupling and recombination change the CMB in moderately messy ways. What you would really want is evidence from just basically the cosmology data sets that you have this period of early acceleration, and that does not exist. If you look at the CMB large-scale structure by itself, there is no evidence for this early dark energy. The only way you can get evidence is if you jointly fit the low redshift data and this cosmological data, and that's kind of contrived, because that's what the problem that this has been set up to solve, and then you can get a few sigma better results. Is it sample variance? If I was a nice person, I would have put one of Dragon's plots here, but I put my own because I'm not a nice person. This shows here it's not sample variance. Basically, if you measured H0 in different patches of the universe, you would not have a fluctuation that's big enough to explain the fluctuation that we see. Different patches of the universe, would give you different H0 values, just because the universe is different densities and different patches, but that's not enough to explain the Hubble parameter. So this brings me on to why I'm talking about this. We had a brainwave. It happens very rarely, which is why I'm excited about it. But all of this is talking about the distance redshift relationship. But when the universe is expanding, not only does the distance redshift relationship change, but energy densities reduce as well. The expansion of the universe causes the energy density to drop. So actually, you can write down a way of measuring the Hubble parameter purely based on energy densities without going into the distance redshift regime at all. And you can think of this by writing down from your fourth year cosmology class the critical density, and then writing the critical density as the physical density of photons in the universe that we know from the CMB, the ratio of baryons to photons that we know from Big Bang nucleosynthesis, the baryon fraction, and omega m. And we've just seen from the Alcock-Paczynski effect that omega m comes from voids in BAO, just looking at the relative sizes along and across the line of sight. So the key thing we need to measure H0 is a robust way of measuring the baryon fraction. And it just so happens that the gold mine of a galaxy survey can provide this for you. And it does it in a really robust and clean way. So remember how I said before about how in the very early universe you have a field of baryons and a field of dark matter, and they grow together to give you the perturbations. The fraction of energy density in the universe that is in the form of baryons compared to that of in the form of dark matter will change which of these fields is most important, how much each adds to the potential when they come together and give you the final perturbations. What this means in practice for the power spectrum is that the amplitude of the baryon acoustic oscillation signal tells you the baryon fraction. How big those oscillations are compared to the rest of the power spectrum really comes from how these fields have grown together, which has been most important when you combine them to give the gravitational potential that all of these perturbations are growing through. And this is actually quite a clean way of doing it, because the physics is clean. You've just got these two fields growing together into one combined perturbation field, and the amplitude of the oscillations in it depends on baryon fraction. So this is now a stage one idea, okay? We tested it on cosmological simulations, and it turns out that yes, from the power spectrum, we can get the amplitude of the baryonic material, basically the baryon fraction, really cleanly by looking at splitting the power spectrum into baryon and cold dark matter components. voids, BAO, Alcock-Paczynski, give us omega m. Put all of this together and you've got a stage 2 analysis, which is a practical application of this. And our value of H0 lies exactly between the current tension values. But this is just with SDSS. Sorry, it's that one. With DESI, with Euclid, we will do better. Actually, we can just keep adding in power spectra because we're only just measuring the BAO. We don't care what redshift they're at. We can normalize all of that out. We just need volume of the universe. And we can get this H0 measurement down to sub% level, at which point we have a third way of measuring H0, which is very, very different from the other two. And so I'm super excited about this. And if I wasn't here, I'd be like, you know, causing my students' life to be a misery in getting this working. I'm joking. We don't do that. Okay. All right, so that's it. You're all free to go. See you at 9 a.m. for a statistics lecture.
Thank you all. We do have some time for questions. Okay.
Does this measurement depend on the model of dark energy?
Sorry, does it depend on the model of dark energy?
Yeah.
It will very weakly through this. This omega m measurement from the Alcock-Paczynski, it's only just measuring omega m if it's lambda. If it's something other than lambda, we have W coming in to this measurement as well. But that is really weak. The constraint on omega m is strong. So we only need a really weak prior on dark energy, and it's not a problem. When we have this equation at the moment, the limiting factor in the measurement is really this amplitude of the baryon signal. This is like, imagine none of these error bars of these three matter compared to the error bar here.
When would you include? When would you like add the early dark energy, like what era? Would that be like during inflation or?
No, early dark energy kicks in after matter radiation equality, before decoupling.
Oh, okay.
And it can't kick in during inflation because you don't want to mess up Big Bang nucleosynthesis. And inflation is a period of acceleration that you don't know how big it is anyway. So it has to happen after that, while you're in and after matter radiation equality. It has to happen at this point where this spherical shell is being blown out, because you need to basically increase the size of this shell being blown out and accelerate the universe such that it blows out more than you think it would if you analyzed it without it being blown out.
Sounds good. Thank you.
You mentioned earlier in the talk that any measurement of H0 depends on some absolute measurement, whether it's the CMB temperature or the sun-Earth distance. For this third method, is that absolute measurement the baryon fraction, or is it something else?
No, it's the CMB temperature.
Okay.
It's the same as the CMB. So it's basically, this is the photon density again, coming from the CMB temperature and the black body assumption. So in that sense, if we had got the CMB temperature wrong, this would also be wrong. It would be wrong in a slightly interesting, different way to the way the CMB is wrong. But yes, you do always need that absolute measurement as a basis.
And this third measurement starts from the CMB temperature and then just takes a different route to H0 than the traditional way to
exactly
from the CMB.
Yeah.
Cool.
Yeah. What I like about it is it's singling out exactly what's happening through this. This is about as simple equation as you can get, right? You can cancel out this, you can basically cancel out this. You find it's just basically the critical density written out in some expanded way.
Okay, so time for one more question.
How helpful is including bispectrum in this analysis? Is it just breaking the degeneracy between F and sigma 8?
Which analysis are you asking about?
The very last slide, like putting all things together. You
Oh.
mentioned only using power
Oh,
spectrum.
yeah, no, we don't need the trispectrum for this. We're not doing it on power spectrum shape or trispectrum shape. If you can find some way of better and more cleanly measuring the baryon fraction, that would help us. But otherwise, I think we're good. This is CMB temperature, Big Bang nuclear synthesis. There's no real other way of doing this. Omega M, I think the Alcock-Paczynski effect is a very clean way of measuring the matter density. We could use other matter densities, but what's good about this is it doesn't depend on early dark energy at all. It's pretty much a pure late time, low redshift measurement. Even the CMB temperature, although it's a CMB temperature, it's a present day temperature. So translating this to a photon density, you've done nothing about going to the last scattering surface and coming back. You're doing everything locally. Big Bang nuclear synthesis, admittedly, that's at high redshift, but I think that's clean and safe physics. These are both low redshift measurements. So you're not doing anything really around this early dark energy epoch.
Okay, thank you.
Okay, let's think through one more time. Yes. Oh, did you want to say something?
Just a quick round of announcements. So for fun tonight, some people are interested in seeing teams fighting for a position at the World Cup, specifically South American teams. So if you're into that, we'll probably be around drinks starting at 7 p.m. Brazil, Ecuador, starting at 9 p.m. Chile and Argentina. So that's one thing we can do tonight. Another possibility is at 8 p.m., people are interested in karaoke at this place called The Cirque, spelled The Circus, but without US. So if you're interested, well, yeah, come talk to us. And more officially, tomorrow we'll have a cosmological soccer match. And for that, we will really need your help. That will be at 3 p.m. at a place called the Mitchell Field. If you don't know how to get there, you can meet us here at 2:30, more or less, and we can take a bus there. The bus is free. And we're probably doing gravitational waves versus electromagnetic counterparts. So if you really want to defend your team and make sure you win, please attend. And I think that's it. Any other activities? That's it, right? All right. See you guys in a bit.